Good morning, gentlemen. So today is Thursday, May the 14th, and today we are going to talk about waves again, but more specifically, light and the idea of refraction. All right. Now remember that the refraction of a wave is the bending of a wave, the change in direction of a wave when it strikes the boundary between two different media. All right. So, for example, if a light wave in air strikes a piece of glass or some other transparent substance, it will actually change its speed and therefore change its direction. Now, mathematically, the relationship between the direction of the wave in one medium and the wave in the next medium is called the absolute index of refraction. All right, and that's what we're going to talk about today. All right, this process of refraction and the behavior of waves when light waves when they actually strike the boundary between two different media. Now, by definition, the index of refraction is referred to as the absolute index of refraction, and it is abbreviated with the lowercase n. And the absolute index of refraction of a substance is simply the ratio between the speed of light in a vacuum, which we all know is c, or 3.00 times 10 to the 8th meters per second, right? Remember, that was found on the front page of your reference tables, right? C is 3.00 times 10 to the 8th meters per second. And its speed in that substance, all right? And so if you were to look at this mathematically, N equals the ratio of C over V. Now, it turns out that there are a number of different absolute indices of refraction given to you on the second page of your reference tables. All right. Now, these are absolute indices of refraction of light at a frequency of 5.09 times 10 to the 14th hertz, and you've got air, which is 1, corn oil, diamond, ethyl alcohol, crown glass, flint glass, glycerol, lucite, quartz, sodium chloride, salt, in other words, water, and zircon. All right, and they're all listed there. Now, interestingly enough, because the speed of light in a vacuum is a constant, all right, c, if we rearrange this equation, we can get c equals n times v. All right, or the speed of light in a vacuum is equal to the absolute index of refraction of a substance times the speed of light in that substance. All right, and even more interestingly, we can then set up a proportion between the absolute indices of refraction and the speeds of light in certain substances. So N1, V1 would equal N2 times V2. All right. So there it is. Now, these two formulas, by the way, are found in various forms on the waves, or in the waves section, all right, right down toward the bottom. The first one is here. Absolute index of refraction is C over V, all right below the law of reflection. And then down here on the bottom, although it's written in a different way, the absolute index of refraction of 2 over the absolute index of refraction of 1 equals the velocity of 1 over the velocity of 2. And you can also throw some wavelengths in there too, because we know that those are proportional as well. All right, but those formulas are given to you, even if they don't look exactly like the one that you see here. So let's see how we can use these formulas in a given question. All right, so we've got, what is the speed of light in water? Okay, interesting. All right, so in order to address this, we're going to start out with, oops, I got to do the pen thing. So I'm going to start with the fact that I know that c, the speed of light in air, is 3.00 times 10 to the 8th meters per second. And I can look that right up on the front page of my reference tables. I'm looking for the speed of light in water, so that's going to be my value of v. And what I can do is I can look up the absolute index of refraction of light in water on the second page of my reference tables. And if you look carefully, right down toward the bottom, the absolute index of refraction of water is 1.33 here. Now this, by the way, is a ratio, so there are no units. That's why we call it an index as opposed to a variable. So anyway, we know that n is, according to the equation, is equal to c over v, and therefore v is going to equal c over n. All right, and so now all I got to do is plug and chug. I get 3.00 times 10 to the 8th, that's a lousy 10, divided by 1.33. And if I do the arithmetic right quick, that's going to be, oh no, my kid stole my calculator. So 3 divided by 1.33 is, so 3 over 4/3 is 3/4 of 3, whatever that actually comes out to be. All right, let's, we'll keep those for now. We'll get our handy dandy calculator out. 3.00 10 to the 8th divided by 1.33, and bam, we get a big number. All right, it's going to be, let's start this back up again. It's going to be, whoa, what do we say, 2.26? Times 10 to the 8th meters per second. Okay, so 2.26 times 10 to the 8th meters per second. That's awfully sloppy. It looks like it was written by a first grader, but you get the idea, I hope. All right. Okay, so that's example number 3. Now, well, let's go back and examine this a little bit further. What other quantities can we relate to this absolute index of refraction? Well, if you go back to the idea of the bending of the light waves, all right, you realize that there are certainly angles that are involved in this, the angle of incidence, the angle of refraction. And it turns out that a guy by the name of Joe Snell came up with what is today known as Snell's Law. And this states that the absolute index of refraction of a substance, for the incident substance, I should say, times the sine of the angle of incidence is equal to the absolute index of refraction of the refracting substance times the sine of the angle of refraction. And this is also found right on your handy dandy reference tables. All right, n1 sine 1 equals n2 sine 2, theta 2. All right. And so there is Snell's law, all right, the relationship between the absolute index of refraction and the sine of the angle. Which brings us to example number 4, all right? In this case, let's put Snell's law into action. We've got the question, what is the angle of refraction of a ray of light traveling through air? All right, so here is, so what is the angle of refraction? That's going to be my big fat question mark. Traveling through air, that is, so for air is going to be my first substance here. And so if you look up the absolute index of refraction of air, you're going to find that it's 1, all right, that's on your reference tables. Which is incident upon a piece of lucite. Now, the first thing that you should do is go to your reference tables and find lucite on the table of indices of refraction. And if you do, you'll find it right here, and you'll find that the index of refraction here is 1.50 for lucite. And so here we go. N of R equals 1.50. All right, and then we're looking for, we're looking for the angle of refraction. We know that the angle of incidence is 60.0 degrees. Now, using Snell's law, we know that Ni times the sine of theta I equals R times the sine of theta R. All right, and so theta R is going to equal the inverse sine. All right, that's sine to the negative 1th of Ni sine theta I divided by NR. Now, Ni is equal to 1, so that's easy peasy. So this is going to be the inverse sine of 1 times the sine of 60, come on, over 1.50. All right, now the sine of 60 is 0.8660 times 1 is 0.8660 divided by 1.50 gives me, let's see, so this is going to be 60, we'll take the sine of that, right, 0.8660 divided by 1.50, boom, 0.5774, okay? And so then the inverse sine of that is, oh, I can't do inverse sine on this? Is that what this is? I don't know. No, that can't be right. Oh, well. I don't have a calculator with me, but you can hopefully figure this out. Whatever it is. Let me go back to this. And so it's going to be the inverse sine. Hello. The inverse sine of 0.577. I think it said. I think we rounded it to 4. All right, whatever that comes out to be. All right, I don't know the answer right off the top of my head. Stay right here. I'll be right back. Okay, I'm back, and I have a calculator that my kids stole off my desk. The sine of 60 is 0.8660 divided by 1.50 is 0.5773, and if I take the inverse sine of that, I get 35.3 degrees. All right, so this is 35.3 degrees. That's again, it looks like it's written by a 3rd grader, but okay, so anyway, now the next thing, total internal reflection. As a light ray travels from a substance with a high N to a lower n, the refracted ray will bend away from the normal, okay? And so let's say, for the sake of argument, that you've got a surface here, all right? And I'm going to draw the normal line. All right, and let's say, for the sake of argument, that the a ray of light comes in at this angle, and it'll bend away. Okay. If I then increase the angle, we expect that the angle of refraction will increase as well. If I do that one more time, eventually I'm going to reach an angle of incidence that's going to give me an angle of refraction that's 90 degrees. Okay? And so now the angle of refraction is going to be 90 degrees. This angle, whatever that angle of incidence is with the light blue line there, that's going to be called the critical angle. Okay? Because any ray of light that now strikes it at an angle of incidence greater than that is not going to be refracted, it's actually going to be reflected. Okay? Again, if we were in our classroom, I could show you this with a laser pointer. You start out, here's the surface, water to air. As the angle of incidence increases, eventually you're going to strike and then bounce back into the water. So, as a ray of light travels from a substance with a high absolute index of refraction to one with a low absolute index of refraction, the refracted ray will bend away from the normal. If the angle of incidence is increased, the angle of refraction will increase. All right, that makes sense if you look at the diagram that we've got down here in the corner. Now, eventually, you're going to reach a point where the refracted angle is 90 degrees. And at that point, the angle of incidence, come on. The angle of incidence here is going to be referred to as the critical angle. But beyond the critical angle, and this is where it becomes important, beyond the critical angle, you're going to end up with reflection as opposed to refraction. Okay, that formula that you see on the very, very bottom is the formula for calculating the value of the critical angle. Okay. Now, this is not given on the reference tables. They would expect you to be able to derive this because what is the sine of 90 degrees? 1. All right, and so that's they don't leave you with that. In any event, so sine of theta c is equal to 1 over n. That brings us to example number 5. All right, let's change our pen color back to our good old red here. And so what is the critical angle of incidence in a diamond? Okay, and for the love of God. All right, so the critical angle is our big fat question mark here. And so we go to the absolute index of refractions, and if you look up the value for diamond, you'll find that it is 2.42. All right, 2.42. All right, and so the sine of the critical angle is equal to the inverse of the absolute index of refraction. Therefore, the critical angle is equal to the inverse sine of 1 over, in this case, 2.42. And so the critical angle is going to be, let's see, 1 divided by 2.42 equals 0.41, blah, 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 blah. We'll take the inverse sine of that, and we end up with 24 degrees. Okay, that's a fairly small angle. All right, as a matter of fact, if you do the same kind of calculation for any of the other substances on this list, because their indices of refraction are so much lower than diamonds, the critical angle is going to be much, much bigger. Now, what does this do for us? Well, think about it. A diamond with a very low critical angle is going to have a lot of internal reflection. That's why diamonds are so sparkly. All right. The next highest thing here on this list is zircon. And zircon is often used to make fake diamonds, all right? Sparkly pieces of glass, essentially, that are not real diamonds. Not as sparkly as a diamond, but a cheap substitute, okay? All right, so the answer here is 24 degrees. That is the critical angle of incidence in a diamond. All right. Last but not least, let's talk about the idea of dispersion. When white light strikes a prism, you end up with refraction occurring. And if you send that white light through a triangular prism where there are two different boundaries between air and, let's say, glass, and then glass and air, you'll end up with a scenario where the different wavelengths of light, because they all have different frequencies, will bend at different angles. And so you end up creating a rainbow. The same thing happens in the sky when there's water droplets up there, right? The water disperses the light, and you see the various colors of the rainbow: red, yellow, green, blue, and violet, right? Roy G. Bv, all right? Red, orange, yellow, green, blue, and violet. Okay, there is no color, by the way, such as indigo. Indigo is simply something made up by interior decorators. Okay, so red, orange, yellow, green, blue, and violet are the main colors of the rainbow. All right, somebody needed to put a vowel in there. Some kindergarten teacher, some way back in history, decided to put an I between the B and the V. So, in any event, as the white light strikes the prism, it is refracted. And then when each of those various wavelengths of light strike the other side of the prism, they are refracted again. And that's where you see the big old rainbow coming out on the other side. Okay, so prisms separate what we call polychromatic or many-colored, which is white light, into its component wavelengths, because each one has a different frequency, and therefore it has a different absolute index of refraction. It turns out that red light travels fastest, and because it has a lower absolute index of refraction, it bends the least. And that's why red is found at the top of the rainbow. Violet light, on the other hand, travels slowest because it has a higher absolute index of refraction. It bends the most, and therefore it is found at the bottom of these rainbows. Okay, so that's dispersion, and dispersion is simply refraction of white light. Okay, that's all it is. You're breaking up white light and producing a rainbow from it. Okay, the moment you've all been waiting for. I know that you've been dying to do homework questions for me again. And so your homework, gentlemen, and I'm not sure when this is going to be due, actually. I'm thinking probably Monday, which is the 18th of, the 18th of May. Please have questions 5 through 9 ready to go. All right, so they'll be due on Monday, May the 18th. All right, questions 5 through 9. All right, fellas, happy Thursday and have a great day.